Our universe is not homogeneous. We know it from our experience of the observation of the sky. We see galaxies, we see clumps, we see galaxy clusters, and they must have an origin. The origin of these fluctuations in our universe is one of the big open questions since centuries. Modern science came with a few possible answers, and one of them, called the theory of inflation, says that the fluctuations were generated in the very early universe by quantum mechanics, but by what we call the quantum fluctuations of a scalar field, which is a field like a particle with specific properties. This theory has looked for quite some time as very speculative, but then its predictions started to be tested with increasing precision. The Planck satellite maps the universe at a very large distance from us, corresponding to a very remote time. The Planck satellite provides a map of a region of our universe in a very preliminary stage 13 billion years ago. With this map, we are getting closer to the time at which the first fluctuations could be generated, and we can test different mechanisms with good precision. It turns out that this mechanism, called inflation, relying on those quantum fluctuations and the scalar field, are perfectly confirmed by the Planck observations. Another question is it reasonable to assume the existence of a scalar field in the early universe? Until recently, no scalar field had been observed at all. However, a few months ago, the LHC confirmed the existence of a definite scalar field called the Higgs boson. The Higgs boson shares most of the properties that would be necessary to explain the first fluctuations in the universe from fluctuations of a scalar field. The Higgs boson is not necessarily the precise scalar field responsible for the generation of fluctuations in our universe, but it is one example of such a scalar field. These scalar fields can exist. We have a definite proof of it. Either the Higgs boson or another scalar field could then have been present in the early universe, and then its quantum fluctuation would perfectly explain what we see in the Planck map.